So my name is Christina Baxter, and myself and my colleague Scott are going to talk to you today about unknown chemical threats. So with that said, we are recording this. Hopefully everybody can hear me. I'm going to actually, let's see if somebody can put a note in the questions section if you can hear me. Hear you, Jameson. Okay, hey, Jameson. So I see a lot of our folks on here that frequent flyers come into a lot of these. So thank you for joining us. And we're going to talk today a little bit about unknown chemical threats. And this is one of the things, wow, we don't truly have a whole lot of unknowns per se in the real world because we generally have a lot of ideas about it. I want to talk to you about really more about how do we take the different tool sets that we have and make them work together. So that's kind of what we're going to focus on today. So background for me, my name is Christina Baxter. I own a company called Emergency Response Tips, and I'm a partner in a company called Hazard 3. And so what we do for Emergency Response Tips is try to come up with technology, instruction, and policy solutions for the emergency response community with a focus on hazmat CBRN. So that's where I come into play, and then I'll pass it over for Scott to introduce himself.
Morning.
Hotel room.
Yeah, I'm in a hotel room, as you can't see, so hopefully we will not have any interruptions with the Wi-Fi or people trying to knock on the door. If you do, if you hear things, that's the reason why. But so my name is Scott Hartley. I'm the CEO of Proengin. So Proengin as a whole has recently started an effort called the Proengin Academy. And the whole purpose of that is just to provide tools for first responders and hazmat operators on the use of different technologies. And as you will see, this is not just specific to our technology. A lot of the discussions, because there is no single detector that does everything, will involve other detection technologies as well. So that's an important thing for us, is that these are not meant to be sales presentations. They're meant to be technical inputs that can be used by multiple people for training and education, and just to overall help the community as a whole with that. So that's kind of the purpose of it. So we're glad that you are able to attend, and there will be ongoing sessions like this where our goal is to have probably every 3 months or so different technical discussions. So this is one of those items that has been an important one that we always wanted to talk about, is dealing with the unknowns with the devices. And so hopefully you guys will find this very helpful.
Okay, and so following this webinar, this one is like the others being recorded. Proengin will follow up with you about where you can see the recording if you want to look back, or if for chance you missed this, that you can go back and get access to the whole video. At the same time, Proengin is putting out some training certificates. That will take a few days after we're done for them to put together the certificates for the training time and to send those out to everybody. So you should look at that for your email that you use to sign up for the webinar. In most of our webinars, we also include application notes or technical notes, so little white papers that walk you through how to do those. This one does not have one that is going to come out right with it. We are still working on it. As you get into this, you'll see there's a lot of different flow charts depending upon what we're going to do. So I'm going to walk you through how we do everything today, and then we'll follow up in some time with some more application notes, and we'll send them out to you guys when those are available. But I'm going to go ahead and turn off my video and start there so we don't waste all of your data flow. So let's go ahead, and I'm going to turn mine off. Okay, and so we're going to start in and talk about unknowns. So just like with any other incident, we're going to have to arrive on the incident, recognize and size up the event, making sure that you're doing that 360 yourself. Oftentimes, from a hazmat or CBRN perspective, we're not the first person on the scene. And so somebody has already done a size up of the event from their perspective. But as those of you who know me know that there's always been some different issues of not having our eyes on it and making sure that you as the responder to this event do your own size up, because you can't rely on somebody else's mindset and the things that they have in the back of their heads that they're looking for. Establish command as quickly as possible, secure the area, obviously, and then rule out the radiation hazards. We're not going to talk about radiation hazards today. We're going to very focus on the chemical hazards. And so as we go forward, the things that we're really going to focus on are going to be measuring the flammability, the oxygen concentration, the corrosivity, and the toxicity. Because when we're dealing with unknowns, we're very much coming at it from a risk-based approach, meaning we're going to figure out what the flammability, corrosivity, toxicity, and radioactivity are associated with the unknown and make our decisions accordingly so that we can quickly get things in place and continue on that road for identifying the unknown once we've categorized and started moving forward. So when we start talking about the things we're going to talk about today, it's really about that reconnaissance strategy and really making sure that we're gathering the information we need to employ proper risk control measures and making sure that we have a strategy before we go downrange. So that strategy may be as simple as making sure there's not booby traps and things present. Now, we haven't seen as many booby traps as of late as we did in the early 2000s and the late 90s when there were all of the traditional meth labs before we got to the one pots. There were a lot of booby traps back then. Determine if there's threat materials, if they're in the air, they're on surfaces, are they a solid, a liquid, a gas? Where are we looking for them and how are we going to sample them? If possible, we're going to get any opportunistic samples. That means something that's readily available. We're not going into things if we don't have to on that recon strategy, but trying to see things that are outside of the container, taking advantage of that. Most importantly, recording some of the primary information about the scene and the intelligence, whether that's from a traditional camera or a thermal camera combined with a traditional camera. All of these things play a huge role. And of course, identifying any casualties, because we got called there for a reason. And one of the reasons may be that somebody was injured with a release. And if so, that injured person is also providing us with a lot of detection information. But while we do all of these things, we have to keep in the back of our mind all the time to avoid the destruction of potential evidence, because many of the scenes that we come across end up being a crime scene. Okay, so when we develop that recon strategy, it's about making sure that we are identifying the threats within this area and make sure that we're making good decisions based upon basic information about the radioactivity, flammability, corrosivity, and toxicity. And if it is a hazardous area, why are we entering? Is there something we're going to be able to do to change that area as hazardous level? Meaning, if it is something where there's been an explosion and there may not be any way for us to save that chemical into its container, is there a reason for us to go in there? Okay. If we are dealing with something where it's just in a broke pipe and we may be able to reroute, or we may be able to freeze patch, do different things, then there's a great reason for entering, as long as we're able to control the risks. Okay. So what are we going to do when we get there? Okay, what do we expect to find? And what equipment are we bringing downrange with us? Do our people have the training necessary to operate that equipment and interpret the results? And what are we going to do with those detection results? Because a lot of times people take detectors downrange to get an answer, but they don't think first about what that answer is telling them. And that's kind of the impetus behind this whole talk today, is understanding what each of these different capabilities tell us and using that to our advantage. So I'm going to pass this over to Scott.
So when it comes to the detection of different chemicals, as we talked about before, there's not one detector that'll do everything that you need. If a supplier comes in and tells you that, they're lying to you. And this is coming from the detector guy here, but I think it's important in this case, especially, to delineate between your trace detection technologies and your bulk detection technologies. And they each serve an important purpose. In this case, because there's unknowns and you're trying to determine detect to warn and detect to protect. In particular, this is why those trace detectors become an important part of that. That's not to say that bulk in this case do not have use. That's absolutely not the case. but in this case, it's an unknown, and you're trying to assess and come to that. And so what are trace detectors? So they're detectors that have a very quick response time. So less than 10 seconds, in many cases, just a couple every 2, 3, 4 seconds or so of that. Why that's important is you're trying to find the source and determine concentration levels. So if you have a technology that takes 30 seconds to respond and you're trying to quickly go through a room, that's going to be a pretty hard thing. So having a very quick response time is important with them. You want something that's easy to carry, so it tends to be lower weight, more a handheld or something you can throw on, holding onto a strap. With it, and you want continuous sampling, not batch sampling. So continuous sampling is the detector is constantly sampling materials. In the case of your bulk detection methods, you need a very good sample, and usually that sample process takes a while for that to process through the detector because it's developing spectra of various types and then comparing it against a database of being able to do that. With it. Another one advantage as well with these, because you're potentially putting the detectors at risk. For example, if you were dealing with potentially something that was really harmful and that couldn't be easy to decon fully, like a chemical warfare agent, for example, you don't want to have $200,000 piece of equipment, right? So you want something that gives you quick data, lets you assess the situation, determine concentration levels, and then isolate. In this case, because you don't know what it is, it's giving you a series of data points that you can then use to go through a spreadsheet that or a process that we're gonna talk about in more detail to get to the point where you can help identify there with there. And then obviously not knowing where even the source is in many cases, bringing in a bulk detection method where you need to have a good sampling method becomes a little bit problematic, right? So if you don't even know where the material is, you need a good sample in order for any of those things to work. So being able to utilize these trace detectors to identify the source, and then you can get good samples that you can then use to bring some of those other equipments down the range to do your validation and your detect to identify. Go ahead.
Okay, yeah, there we go. Okay, so when I'm talking about the Recon equipment that I like to think of, obviously for me, I really like to have a thermal camera. And one of the reasons I like that thermal camera is I can start looking whether there's reactions going on. So either I can see something that's very hot that shouldn't be, or very cold that shouldn't be. So I have my exothermic or endothermic reaction. I can start looking at a puddle and say, okay, I have a liquid spill, but is it a high vapor pressure liquid? Is it evaporating? And if it is evaporating, I should see a nice cold line right above that puddle. And then, of course, I like to bring in my papers. So indicating papers are a great tool to use for any of your unknown types of situations. So I generally use pH paper, both wet and dry, M8 paper, KI paper, and then F paper. And then 4 gas detectors. So any of our electrochemical cells that we may have available, I also want to use my flammability for the LEL or LFL, whatever you call it. The oxygen sensor, which is great for measuring oxygen, and that's about it. Okay. The photoionization detector. So I think all of us rely on our PIDs a lot. I use the flame spectrophotometer as well. And then radiation meter, obviously, just to rule out that radiation hazard. So when I look at these detectors in terms of the different risks that we're looking at, the radioactive risk, I'm using the rad meter alone. The corrosive risk, I'm using my pH paper and I'm using my F paper. Then we start to get a little bit more interesting. So for my toxic risks, I'm using, anytime my PID is hitting above 100, I'm assuming it's likely toxic. Okay, when I get my M8 paper and it soaks in a material, I'm figuring it's probably organic and it may have some toxic characteristics. Any of my electrochemical cells going positive, okay, regardless of whether there's a cross sensitivity, may tell me about toxicity. And then my flame spectrophotometer, any of the phosphorus, nitrogen, arsenic, or sulfur channels going positive. I also will use my KI paper a lot for this. So my KI paper is looking for oxidizers. And now it doesn't get every oxidizer, but it gets a lot of things. And oxidizers really are the things that make the reaction so much worse. And then flammable, we have a lot of information coming from here. So as we get into our LEL sensors, we look at LEL sensor greater than 1%. Okay, our PID greater than 100 is likely flammable. Our pH being 8 to 12, so in that relatively neutral, just slightly into the basic area, are generally combustible and flammable. M8 paper that soaks material in is generally combustible and flammable. It's an organic material oftentimes. A CO sensor that says positive. Oftentimes that could be hydrogen, acetylene, ethylene, those types of materials. Then of course the flame spectrophotometer on the CH channel. When it hits that CH channel on a flame spectrophotometer, you know it's got a high level of organic material in the area that's charring and giving you a lot of particulate and cooling down the flame from the burning. So oxidizers also play a role here. So the KI paper plays a role in terms of if I have something flammable, is it going to become more flammable? So when I start looking at just these basic tools, there's a lot of information that I get about our different risks that we have to deal with. So I'm going to start out with a few of these, and then Scott and I are going to go back and forth so you don't get sick of just hearing a bit from me. But reality is, when I use my thermal camera, it's all about figuring out what I can see. Now, when I'm doing reactions, the containers can so hotter or colder than they should be, so I can see whether there's a reaction going on. As we said, that cold line above a liquid spill tells me that I have a vapor forming liquid. Okay, so now I know that I have a liquid that has a moderate to high vapor pressure, or I wouldn't be able to see the line. And then I can look at enclosed containers and say, can I see the product line? And if it's really distinct, does that mean that I just had material that was evaporating? And should I have had material evaporating? And so those color differentials tell me a lot. Personally, I like using a thermal imaging camera that has both the thermal and the visible pictures. So when you snap the one, it snaps both. And that gives you the information you need side by side. So when you come out and talk to your other team members, you have those pictures to say, here's what I was seeing, and here's what the thermal was seeing, and getting that information. Now, there are a lot of teams that still use temp guns, and temp guns also work very well, but they're not able to see through as much and get as much information. So a thermal camera, remember, you also have to avoid things that are going to have very glossy surfaces. So things like metals that will give you a flash back on it, so you won't actually be able to see the information. Avoid things that will not have a temperature differential. So different things like that. When we actually use the thermal camera, remember that it's averaging everything between the camera itself and the point you're looking at. So as you get closer, it gets more accurate. Now, the first thing that we're going to start monitoring for is going to be flammability. And that just makes sense in terms of what type of gear are we going to wear. So when I start looking at flammability, I want to make sure that I am always looking at this lower explosive limit or lower flammable limit, and never even take into consideration this too rich to burn. The reason I don't take that in consideration is that can change rapidly. If we end up opening an area and venting, we can actually go from too rich to burn to flammable very quickly, and we don't want to be caught in that point. With most flammable materials, if we can, and if they're not severe skin toxic, we end up going in turnout gear, because that's our biggest risk to us as operators. Now, when we look at this, we have to remember that that sensor is reading a percentage of the lower flammability limit. So when I look at this and say I have a lower flammability limit here, it would show up around 18%, then my reading is going to be 1% of that, or a 10% of that. So if I was saying I'm going to pull people and I had a flammability limit on the low end that was 18%, and I use a 10% reading on the sensor, that 10% stands for actually 1.8% of the flammability of the material in question. And that's why we always use that 10% to pull people, because we don't want to go into an area where things can really start to change rapidly. But the flammability tells me a lot about the material, because where it's measuring in percentages, that means that a material is very flammable or very volatile for me to be able to measure it. So you start looking at chemicals like toluene, benzene, acetone, ammonia. Every one of those has a very, even if they're a liquid, they have a very high vapor pressure. So when I see something that's measuring on the flammability sensor, I know that I have a lot of material making its way into gas phase. Okay, so here's an example of what we would see. So this is just hydrogen sulfide. Hydrogen sulfide's lower flammability limit starts at 4%. 4% is equivalent to 40,000 parts per million. So if I'm reading 10% on my sensor, that actually stands for 4,000 parts per million, because remember, it's reading a percentage of the LFL. So 10% of the 4%, which would be 4,000 parts per million. Now, that's telling me also, when I think about that, that the instrument's limit of detection at 1%, because remember, these measure in percentage units, that 1% is about 400 parts per million. So I would have to have at least 400 parts per million of hydrogen sulfide in the space for the flammability sensor to read it. Okay, that's an important thing to think about when we start looking at what is telling us about flammability. Because I'm going to start seeing things on my PID that make me think about flammability long before I'm going to see it here. And so I just want to make sure everybody keeps that in the back of their head as we go through this. Now, the other things that start giving me information, okay, we talked about this a little bit before, but when I'm at that 1%, remember that that's going to be, for hydrogen sulfide, 400 parts per million. My PID, if it hits over 100, I'm starting to think flammable material because of its ability to go up. My pH between 8 and 12, generally an indicator of combustible and flammable materials, and sometimes even lower. Okay, my M8 paper soaks in combustible or flammable material. My CO sensor goes off for some. Okay, my CH channels on the AP4C, and my KI paper. Each of these things is giving me a little bit more information about flammability. And while we always rely on our LEL sensor, we have to remember that while we are using that as our go, no-go on terms of different types of protective clothing, we have to remember when we're looking at an unknown that may be in a smaller amount, that these other things also give us a bit of information. Now, oxygen levels is another important one, and one that we have to think about a little bit, because whenever we're teaching a class and I ask about oxygen levels, people want to use an oxygen sensor for air displacement. And we have to remember that the oxygen sensor is only reading oxygen, which is only 20% of air. Okay, so we have that rule of 5, the factor of 5. So if we have a threat that's in there, it's going to displace air by 5%, which is only 1% oxygen. So every drop of 1% on your oxygen sensor represents 5% of something else. Now, when you think about that and think about 5% of something in the air being 50,000 parts per million, for any of the threats of interest, 50,000 parts per million is way too high to be even considering. That's way above IDLH for most everything. And remember that the oxygen sensors are generally set for a factory alarm of low oxygen at 19.5%. So you're way beyond that by the time you actually see a sensor going off and alarming for something else in the air. But you could watch that. The other thing I want you to keep in mind is that most sensor manufacturers put in what's called a dead band. And so from that 20.9 or whatever your standard reading is, down 0.2 measurement units, you actually don't see any flickering. So when I start thinking about that, I have to remember that that 0.1 is around 5,000 parts per million. So even if I was to use my oxygen sensor, before I actually saw a change in that 20.9, which would be a 20.9 drop to 20.7, that's recommended, that's 10,000 parts per million of something else. So that dead band is something that has to be taken into consideration when you're starting to use that oxygen sensor outside of its designed purpose, which is to measure oxygen concentration. Because a 0.2 drop in oxygen concentration is not going to bother us, but a 0.2 increase in something else, filling that space, is. So we have to be very careful there. Now, I think I'm going to talk about pH paper for a little bit. And I know all of us use pH paper all the time. But generally, when I hear somebody using pH paper, they're usually saying, hey, it's an acid or it's a base or it's neutral. But we don't go any further into that. And I like to use my pH paper that allows me to get a little bit more information. And so here's how I use it. I actually start with pH paper dry, okay, and I put that in the solution. If I don't see a change, okay, then I assume it's either not corrosive, meaning it's pH neutral, or it's a corrosive, but it's of ultra high purity. So I get something like oleum, like that's just sulfuric acid, which had sulfur trioxide added into it to keep it from being able to bring on the moisture in the air. And so when you start looking at these things, just remember, with the pH paper is dry, you can't rule out an extremely high concentration corrosive because you need the water for the pH paper to work. So then come in and have my pH paper wetted now and stay above any solution, and then figure out right away, is the liquid corrosive with a vapor forming off of it? Okay, and when you do see your pH paper start to change color above the solution, just remember, the farther away you are from the solution when it changes, the higher the vapor pressure. So when we start looking at that, we can say if there's no color change, the liquid's not corrosive. And if the liquid is, or if the liquid is corrosive, it's got a very low vapor pressure. So in this case, a good example would be sulfuric acid. I can hold wet pH paper right above sulfuric acid and very rarely, if ever, see a change because the vapor pressure of sulfuric acid is so low that we don't see vapors coming off of it until we do something like heat it up. Okay, then I go and take my wet pH paper and put it right into the solution. If I put it right in and it changes color, then the liquid is corrosive. And we can start figuring out things about concentration if we know the pH. We can't determine the concentration without a little bit more info. If we put the wet pH paper into the solution and there's no change at all, then we assume the liquid's not corrosive, it's pH neutral. So this is giving us quite a bit of information right off the top. Now, we also, in gases, so let's say we don't have a liquid spill, but we have a gas phase spill. We just wet our pH paper and put it in the air and say, is that a corrosive gas? And if so, we're going to figure out pretty quickly that it's a corrosive gas and what level of pH it's giving us. Same type of thing if we have a solid. We can wet the pH paper and touch the corner of the solid and say, does it form a corrosive with water? So do I need to wet my pH paper? Well, yes and no. You want to leave it dry to determine a little bit about concentration so we can get that ultra high concentration. It can be very problematic. Or we'll have it wet to make sure that it's working. Now, the other thing and why I like to use pH paper that has the different color changes for different levels is it allows me to start thinking about what types of chemicals would fall into each range. For instance, when I get a pH that's in that 0, 1, 2 range, I'm usually thinking inorganic acids. So things like sulfuric acid, nitric acid, hydrofluoric acid, hydrochloric acid, and phosphoric acid. When I get a pH that's between 3 and 4, I usually start thinking of things like organic acids, so acetic acid, carboxylic acid, citric acid. All of those things start falling into those organic acids or acids that are not giving us the strength that we get in those inorganic acids. When I get things that are just slightly acidic, I usually think of organophosphates and aldehydes, because when they break down in the solution, they start to give us a slightly acidic range. When I get things that stay pretty neutral, generally I'm thinking organics or biologicals right off the bat. And I start looking through which organics fall there. And generally it's those organic solvents or the hydrocarbons that we deal with, okay? Ketones, oxidizers, a lot of those things. And I can start pulling that apart by looking at the other types of papers that we have. When I get up above 8, I start thinking of those alkali or alkaline earth hydroxide. So we might have something like a lithium hydroxide, those types of things, calcium hydroxide here. Some of the carbonates and sulfides would fall in here. Organic peroxides. When we get between 8 and that 10 range, we're talking about ammonia, things of that nature. 10 to 12, we go into our amines. So ammonia being the smallest of the amines, or the most basic of the amines. Everything else we start going on, methylamine, ethylamine, all of those types of things. And then we get the really strong bases. I'm usually thinking potassium hydroxide, sodium hydroxide, those types of things up here at that 13 and 14 range. So you can see that you can start to pull apart your chemicals even with the very basics of pH paper. Now, obviously, when I have a high pH in that 0 to 2 to 3 range, the first thing I do is pull up my F paper and make sure that I don't have hydrogen fluoride. Now, F paper, you'll see a lot of times it'll say needs to be pre-activated with hydrochloric acid. And I get this question a lot. Do I really need to do that? Well, it depends upon what you're measuring for. If you only want to measure for fluoride, for hydrogen fluoride, for whether it's gas phase hydrogen fluoride or it's HF in solution, then no, you do not need to activate your paper. You can dip that into the solution and you'll get that yellow color change you see down below. Okay, that's just me dipping it into a hydrofluoric acid solution. Now, if you want to measure fluoride ions, then yes, you do need to activate it because it needs to be acidic to work. So fluoride ions, things like fluoride-based toothpaste, fluoride-based mouthwash, those types of things, you do want to activate it. Now, does it have to be specifically this concentration hydrochloric? Not really. I actually usually just take a couple drops of hydrochloric, put a little bit of water with it, dip it in there, get it acidic, and then put it on the others. And then I can see if I have fluoride ions present. So quick, easy way to do it. But if in the emergency response community, we're really generally looking just for the HF. And in that case, you don't need to activate it. You will see sometimes, and when I'm using HF lately, one of the most common places that I find HF is in the etching industry. So in the semiconductor industry or the people who are making computer chips, a lot of HF in those areas. So when you think about that, I know nobody wants to go to a store like Michael's on a Friday night, but that's where we end up finding a lot of HF. Because in the arts and crafts community, it's used in glass etching. And so most of the time, it's just called glass etching medium. And it doesn't say until you look into the really small print that it's hydrofluoric acid. And that's one of those things that's just waiting for an accident to happen. Because we all know when we have an HF incident, it can be very problematic. Because at first, you don't notice the problem. And sometimes you don't notice the problem until it's too late. So with this case, I like using my F paper right after my pH paper and making sure, or at the same time even, that I have that there. Now, so just kind of an example right quick. If we were to have a spill, and let's say we have a mixed load full of a lot of these inorganic acids, and we're not sure which one of the containers is leaking, but we know, we can see right off the labels are hydrochloric, nitric, phosphoric, sulfuric. And so what I just did is, put down the most common concentrations you'd come across in the field, and then what their vapor pressures are. And you can see right away that for all of these with pH dry, because they have significant water contents, then you're going to have your pH change, and it's going to change to a bright red, and it's going to be that 0 to 1 to 2 range. When I wet the pH paper, I'm going to get that same result in the liquid, but above the liquid, only the top 3 are going to change, and that's because of their vapor pressure. So when I look at the vapor pressure, I think we all think in our heads when we see fuming nitric acid, we see that orangish, the nitrous oxides gases above it. That's telling us that it's fuming, and that's actually the least of the vapor pressure. So hydrofluoric's much more higher vapor pressure, and hydrochloric higher as well. So when you start thinking about that and the fact that you see these ones, just remember these ones aren't as available to the naked eye, but are much higher. Okay, so these ones above liquid, I'm going to miss out on phosphoric and sulfuric. So now if I had all of these and I needed to figure out quickly which one it was, we have a couple of options. Okay, and so if I'm just going to divide them out and figure out, okay, which material do I have leaking, and just pull each of these containers off, figure out which one has the leak, and then deal with that and pump it off to a new IBC or whatever type of container I have it in. I'm going to talk about option 2 first, because that's the most traditional way. So in this case, I would have done pH paper first and found out whether I had a vapor forming or a non-vapor forming liquid. Okay, if it was vapor forming, the first thing I'm going to do is F paper and make sure it's not the HF. If it's not the HF, now I'm down to hydrochloric and nitric. I have a couple of different things I can do. I always keep pieces of aluminum foil, and so you can actually take a piece of aluminum foil and just put it with a drop of the material and say, does it start reacting on the aluminum foil? Hydrochloric's the one that will do that. Another thing you could always do is if you, for some reason, had ammonia out there, like an ammonia hydroxide solution, you could wet something with the ammonia hydroxide and put it right above the hydrochloric and see if they reacted. Then you'd see a white gas coming on. It's really particulates it's forming. Sulfuric acid, if it was that, I could pull it out and put a drop on some sugar, and you'll actually start seeing a reaction which causes production of carbon, and then production of carbon dioxide and sulfur dioxide. So you see a black material starting to react. And then if it was nitric acid, the standard reactions with copper filings. So if you keep a little thing of copper filings with you and take a drop of that nitric acid, put it on a piece of copper, you'll see that turning to a blue-green pretty quickly. And phosphoric acid, we couldn't see with any of them. The more modern approach that I like to use is just pulling out my AP4C. And with that, I won't be able to see the hydrochloric. I'm going to use that as my holdout. My hydrofluoric, I'm getting on my F paper, but my nitric, I can see the nitrogen. My phosphoric, I can see the phosphorus, and my sulfuric, I can see the sulfur. And so this is actually a flame spectrophotometer, so it's just looking, and Scott will talk about it in a bit, but it's looking at those elements, nitrogen, phosphorus, sulfur, and arsenic, and it's telling me whether they're there. And so I can quickly go through and say that they are not there. Now, the interesting thing is, even though the vapor pressures are these low, we can actually measure some of these in vapor pressure, but using the wand that comes with it. And so we'll talk about that a little bit. We can actually measure it as a liquid and just take a little bit of the sample, put it into the interface, and you can actually see it change. It takes about 2 seconds or so to do the sample. So really different ways of approaching it, but getting the same answers and determining which one's the leaking culprit and then dealing with the call. I'm going to pass over to Scott at this point.
Thanks, Christina. So continuing on relative to the different types of detectors that can be utilized to help identify these unknowns. So the AP4C is a nice tool to bring into there. So how it exactly works, for those of you that aren't familiar with it, is what we do is we, when the device turns on, there's a fan that is pulling air through the device. So it's a continuously sampling device. We're outputting the information coming from the detector, so summary data every 2 seconds. So we're telling you what went through the detector on the last two seconds. What we're doing in order for this process to work is we're introducing hydrogen, and then that creates a flame. And so what that does is that excites the incoming materials. And so we're running on a principle: when you excite atoms, certain materials will produce visible light when they're going into the relaxed state. And then what we're doing is we're collecting that light information, we're analyzing it through a series of sensors, so through some optics, and then we are actually converting that information to electrons that we can process through our processor to be able to do that. So each material has the way I like to describe it, it has its own unique response on the visible spectrum. So there's a fingerprint for each of these materials that's specific to that chemical, to that atom, and only to that atom. So therefore, we don't have false positives. So we have the accuracy of your GC mass spec from the standpoint of we're able to identify materials very clearly, or this process allows you to identify materials very quickly and fast, continuously with that. And then you're able to input those. What we aren't able to do, because we're only focusing in on the light spectrum or the visible spectrum, is be able to identify the specific compounds. And the reason being is we just aren't collecting enough information that allows you to delineate between those different materials. And so that's why a lot of the bulk processes take a while, because they have to collect information over larger spectral areas and then compare it against a known database in order to match those peaks in the transmission and absorption spectrum with those. The advantage of this is that because you're able to do this real time, you're able to get information that's important for assessing the situation. The second benefit of this approach is the amount of light can be quantified. So from that standpoint, the more light that's present, the more atoms that are present, the more light that's produced can therefore be quantified into concentration levels. And you can start at really low concentration. So in the case of the phosphorus, because that tends to correlate with some of your organophosphates, which tend to be your lowest concentration materials that can cause problems. Thanks for switching that chart.
Sorry.
To be able to identify those at really low concentration. So the system itself can identify starting at like around 1.7 parts per billion, which is a really low concentration to be able to do that, which is needed with those. So the AP4C detector is really looking for 5 main channels of information. 4 of those will correlate to materials. The 5th will create towards your hydrocarbon channel and I can talk a little bit about that. But so we're looking at phosphorus, hydrogen, nitrogen bonds. Really the nitrogen is what we're most interested in, arsenic and sulfur. So those correlate to a lot of, those were originally chosen because of chemical warfare agents, but they also correlate to a number of toxic industrial chemicals and materials with those, and many of those which can be harmful. And these materials are a lot of building blocks used in a lot of different materials, especially I would say on your sulfur channel and in your nitrogen, hydrogen, nitrogen channel. There are a lot of materials that are present in those categories with them as we're doing there. And it's a nice delineation if you have unknowns that you're trying to deal with to get classifications of it. So to go back to Christina's example where you have different types of acids present with it, you're getting a response on pH paper. One of the advantages of the AP4C, if you're getting vapors or if you have to introduce it, and we'll talk a little bit about that, if it's not vaporizing to be able to do that, you could sample those and very quickly be able to delineate between your sulfuric acid, which will hit on your sulfur channel, your phosphoric acid, which hit on your phosphorus, and then also your nitric acid, which will hit on your hydrogen nitrogen. So there's advantages to be able to do that. Now you can do about 47, I think is the last number that I saw with it, different elements with flame spectroscopy process with it. One of the things you can't do is chlorine. The reason being is that chlorine doesn't produce a visible light associated with it that can be captured. It is something that's being worked on for potential variants of it, but that's just something as well to consider. There are, just like with every detection method, there are limitations. So it's important to understand limitations as well as what capabilities are. Next slide, please. So what does it tell you? So first of all, the system, the AP4C, not specific to maybe all flame spectroscopy processes, are able to detect both aerosols and gases. So that's important. There are a number of detection methods that just can't handle aerosols. The reason being is they have, some of those detectors tend to have filters in place to protect the detector from the aerosol. In the case of the system, the AP4 system, is not subject to that. So you can handle aerosols and gases present in those. Some detectors are just specific to gases or vapors with there. So if you know the identity of the gas, then we're able to identify those. Now each channel is set to its own specific trigger amount, and then you get as much dynamic range out of the device that is possible. So since the process is working on the presence of light energy, there becomes a limit to which you can't identify any additional light. So the way I like to describe that is if you were outside and someone had a big spotlight on you at night, and then your friend just held up a small flashlight next to that spotlight, you couldn't see that small flashlight. The same thing basically happens with this type of detection method. There becomes a limit to how much light you can see. When you exceed that, what happens is the detector just starts to blink. So it's letting you know I'm in an overmatched level. And then when you come back into that acceptable range where it can delineate things, it'll start to stop blinking and it'll be in that range as well. So that's also important for large concentrations as well. So what does the screen tell you to be able to do there? So what it's telling you is summary data, so that the AP4C is actually collecting information in the form of parts per million or parts per billion for each of the channels every 2 seconds, and it's displaying you summarized data in there. So what we talked about is each channel has a unique trigger, and then you get as much dynamic range. So what it did is basically broke that up into 6 separate steps. So there are 5 channels, but there's actually a 6 when it's blinking or overmatched. So it's actually 6 delineations with there. So there's a maximum amount that we're able to identify with there. So one helpful tool for this is the chemical companion software, the ERDSS solution. So it's pretty much everyone on this call, hopefully, I think, can be access to it. But there are limitations. It can't go to like Iran or other places like that. But it has this information automatically in it. So if you know the materials you're dealing with or suspected the materials that you're dealing with, you can actually put that in. And the software has it. You can select, for example, this is just showing screen captures from ammonium. And so you can actually select it. So your ammonium, if it's showing, for example, someone says, I'm detecting sulfur, well, there's no sulfur in ammonium. So it's also a safety factor letting you know that. But if you have the readings coming directly off the detector, you can use that to identify, and you suspect the materials, in this case, ammonium, you can actually see the concentration levels relative to TLV and IDLH in there, as well as what the range is for each of those channels. It's all automatically built into the software. It's not specific to the AP4C. It'll show you all detectors that work for each of those materials. Not specific to just flame spectroscopy. It'll have a lot of your single gas meters. It'll have GC mass spec, other types of detectors in there, probably pretty much all of the ones that you've heard of. So it is a very vital source of information to be able to utilize. Next slide, please. So how do we deal with liquids or solids to be able to do there? So what we're seeing here is the standard device comes with a vapor nozzle on it. And then what we have here, which I like to affectionately call the crack pipe, is a way of being able to introduce different materials into the device. So what is shown there on the heater is actually a heater. It's called S4PE with it. So it's green. So if you have an unknown material that you're trying to do, so you pick up that material through the sample scrapers. So first you put the sample scraper on the device, then you're selecting it. And then what you're doing is you're introducing heat. So when that light is on, you pull the trigger. What's happening is you're getting electric resistance through the test strip, and it's heating it up. and then you eventually will get a response based upon the information coming from the thing. If it is in one of those materials that will trigger the device, it will show up. So it allows you to detect different materials that are in a phase that is not off-gassing. I always try to recommend, if you can, use headspace collection methods to try and do that first before you go to using the S4PE solution, just because you get a little bit more operational information relative to concentration. So I always try to say, in open air, try to always do that first. Then the second is to use headspace capturing, and then the third would be to use the liquid sampling of it, just from the standpoint of the detection capabilities. So what does that tell you in the solid liquid mode with it? So what you're doing is, by entering heat to the device, you're changing the vapor pressure, so you're able to identify more materials that may not necessarily be off gas at room temperature. So as you know, especially for some materials have a temperature dependency. So if it's a really cold time period, materials are less apt to produce vapors that you can detect. If it's a really warm time and you're in a low humidity environment, for example, in the desert, you have a much better chance of getting those vapors coming off of the device with it. And so, as you know, different materials have different vapor pressures, and so it determines how much material is going to be able to be off gas. What the S4PE does by adding heat is you're changing the ability to access the material and the vapor pressure. You're increasing the temperature, so that increases the more material that's present, and therefore allows the detector to see it with it. And one additional advantage is you need really small amount of material when you're adding the heat, because you're taking advantage of it. You actually can, down to the picograms in some cases, is all that you need to have present on the sampling dice in order to do it. So there is advantage for really, really trace materials. It does allow you to detect things a little bit more and faster. So continuing on to the PIDs. So PIDs work on a somewhat similar standpoint to what we're talking about, but in this case, you're using a UV lamp. And what happens is that UV lamp ionizes the materials, and then there's current that's produced from those structures. So it allows you to identify materials and concentration fairly quickly with there. So there's pretty quick response time with that. So it's pretty analogous to the FPD or flame spectroscopy. You have a response with PIDs of probably around every 3 seconds or so with it. So the UV lamp is what creates the ionization effect, which then the sensor is able to pick up through the electric current that's produced from it. And so it's a very reproducible, repeatable process. Next slide, please. Now, there are different versions of PIDs, so it's important to understand that which one you're trying to deal with for them. So there's different types of lamps or different wavelengths of the lamps, and they are able to see different types of materials with them. So not every lamp is able to see every material. So it's important to make sure that you're selecting the right detector that has the right wavelength lamp in it in order to go after the target materials that you're interested in. Now, the most common by far is the 10.6 solution. The 11.7 is the reason why it's not quite as common is that they're a lot more expensive, and the lifespan of those aren't really that great. So you're talking about a 3-month or so lifespan of that. The 11.7 does let you see some of your chlorine-based materials, which are important based on the application. So for certain uses, those higher, a little more expensive ones apply, but by far the most common is your 10.6, and it allows you to achieve a lot of your common materials that you'll see with your 5-gas meter. And just like with flame spectroscopy, there are certain materials that aren't ionizable, and so that's also to be aware of with it. I think sometimes detector companies are great at telling you what they can detect and really poor at telling you what they can't. And it's important to understand both sets of data, right? Because you don't want to have a false sense of security that, hey, my detector's not detecting this. Well, it's not detecting it because it can't detect it versus it's not detecting it because it's not there, right? Those are two drastically different sets of information. And so it's important for you to understand that for all detectors. Next slide, please. So one of the additional things we talked about are correction factors. And so the correction factor is kind of a function of the size of your lamp, or the length of the length of the lamp, or the wavelength of the lamp, and the power output of it, and the manufacturers of it that have different performance. So it's really important to understand correction factors, because correction factors will vary based upon the manufacturer solution and the type of lamp that's present. So there is not a universal detection correction factor. So that's one things that you need to be very cognizant of when you're using these, is to be able to do there. And the second thing is some of the PIDs will lose their benefit to quantify at greater than 1,000 to 1,500 parts per million. So really high concentration levels, you have to be cognizant of the information could be skewed from the device. So you need to be very careful with that. And the second thing is, as some of these lamps age, the response can change a little bit. So with it, and then just with 5 gas meters, you have to understand the fact of correction factor. So that's why using the AP4C with PIDs are kind of a nice combination between both of them, because some of your cross sensitivity and correction factors are there. So, you know, for example, if you're dealing with hydrogen sulfide, it has equal correction or cross sensitivity to both your phosphine and your hydrogen cyanide. So the AP4C could really quickly tell you in 2 seconds what you're dealing with. But if you aren't familiar with all the cross sensitivities, that can become a problem with the device, or you thinking it's something versus another, or multiple things are showing up simultaneously. So you need to be able to delineate between this. So the combination of both together becomes a very helpful solution for helping identify these materials.
Okay, I'm going to go on and talk about electrochemical cells, because as Scott brought up a couple of times, there were 5 gas sensors or 4 gas sensors. And what we're generally talking about there are the flammability, which we already discussed, the oxygen sensor that we already discussed, and then there's generally at least 2 electrochemical cells. Your standard configuration comes with a CO, or carbon monoxide sensor, as well as a hydrogen sulfide sensor. And that really comes out of the confined space requirements. Now, I like to think of electrochemical cells as nothing more than a battery. And it's a battery that is run by a different chemical. So all you're trying to do is you have 2 electrodes, and there is a porous membrane that's here, and it's designed so that the electrolyte is matched up with the chemical of interest. And as that chemical comes through, like for this instance, we have CO coming into water, which is making carbon dioxide and the 2 hydrogens. Okay, and then that is actually taking oxygen and the 2 hydrogen at the other end and making water. So we actually look at that reaction, and that reaction is what is giving this amperage here. And that signal that comes out is correlated to a concentration. As you can imagine, anything like this with these reactions is going to have a lot of cross sensitivities. So while it may be a CO monitor for carbon monoxide, we know that it has significant cross sensitivities to hydrogen, acetylene, ethylene, things of that nature. Now, understanding the cross sensitivities is critical. So this is one of the things where when manufacturers come out with new electrochemical cells, they have to come out with a cross sensitivity table to work with it. And I'm a firm believer that a cross sensitivity is just another way of saying, hey, we've got another detector here, as long as you understand and can start using them to your benefit. Okay, now the other thing that we have here is that these are generally sensors that are focused in on measuring in that operational range of interest between the permissible exposure limit and the ideal H level, immediately dangerous to life and health. And what that does is keeps us in a narrow range, but focuses into operational need. So what I've done here is just put together a table, and you'll see the one line here that is response time. And this is where it starts getting critical, because all of the technologies we've talked about so far are pretty quick. So when we talked about our flammability, 15 seconds, our oxygen, 15 seconds, our PID, 2 to 3 seconds, our AP4C, 2 seconds, all of our indicating papers, 2 to 10 seconds, okay? Now we're talking about things that range from 30 seconds to 200 seconds. And so we have to take that in mind. So one of the things that I always do with my electrochemical cells is look at them first and say, are they starting to flicker? Because when I start to see that come up, I know that if I'm seeing it at 2 seconds, I'm going to see a lot at 30 seconds. So I start considering backing down then. But when I start looking at these, and let's just use carbon monoxide as an example, we know it's got a 30-second response time. It's got a pretty good measurement range, but it has a few different things here that we have to consider. So we have acetylene, chlorine, ethylene oxide. All of these things are cross-sensitive on our carbon monoxide sensors. So I've had this one a couple of times where we've had somebody going down range, and it's actually a pre-test for a new auto body shop that was going into business, and they had their CO monitors that were integrated into the walls going off. Now, the problem they had was that as you came in, there was no source of CO in the location. And so they had tested everything trying to figure out where that carbon monoxide was coming from. But in reality, it was a leak in their acetylene cylinder that was causing it. And so everybody kept coming back time and time again and saying, well, there's no carbon monoxide here. And they were correct. But what they should have been looking at was the fact that the flammability sensor was also going off, and they were seeing acetylene coming out. And we see this quite often. It's one of the most common ones, acetylene, or when you're dealing with batteries that are naturally charging properly, some of the batteries give off hydrogen gas when they're naturally charging. So a lot of your lead acetate batteries, if you come in and there's CO going off, but there's no source of CO, well, maybe it's hydrogen. So understanding those is critical. And just like Scott showed with figuring out the concentrations based upon the readings, in the Chem Companion software, all of these things are cross-referenced so that you can use them to your benefit. We also have to remember with all of these types of cells that hydrocarbons can generally become very problematic for the longevity of the system. So we want to make sure that we avoid things like hydrogen and hydrocarbons, and then in some cases, sulfides, to make sure that we don't overwhelm the system and destroy the sensor. Now, this is where it becomes important, because if we look at those response times, we had things that were happening in seconds. So AP4C was about 2 seconds, a PID about 3. Your JCAT or IMS instrument can get around 3 to 5, depending upon which way you're using it. Your indicating papers will actually be between 2 and 10 seconds, but it just took us that 15 seconds for the LEL, so the flammability and the oxygen, to come up. And I'm going to wait a little bit to show you how long that really is to get that 30 seconds to get our first couple of electrochemical cells. So there they came up. Our carbon monoxide and chlorine. Our hydrogen sulfide is going to come up at 35 seconds. And now we're not going to wait for the others, because that's going to take too long. So ammonia is going to be at 60 seconds, SO2 at 75 seconds, and our hydrogen cyanide at 200 seconds. So look at this in a logarithmic scale, so factors of 10. And remember that if I see my hydrogen cyanide sensor going off or starting to have some measurements, at the same time my AP4C or my PID is going off, I've got a problem. Now I need to come back and look at my hydrogen cyanide sensor and say, it could be hydrogen cyanide, it could be carbon dioxide, ethylene, hydrogen sulfide, or SO2, sulfur dioxide. Or if my sensor's going down into the negative range, it could be nitrogen oxide. So you could have something like nitric acid there that's off-gassing. So all of these things play a role, and understanding where they are is critical. Now, you can go into the same software suite and you can pull up your hydrogen sulfide sensor and say, if I were measuring hydrogen sulfide, great, just read it right off the screen. But what if I'm using a hydrogen cyanide sensor to measure hydrogen sulfide? Then I have to use a correction factor. Okay, same thing if I'm using an ammonia sensor to measure hydrogen sulfide. Correction factor, very small. And again, using a chlorine sensor to measure hydrogen sulfide, it'll actually push, hydrogen sulfide pushes the chlorine sensor into the negative. But each of these things allows you to expand the capability of those sensors. Now we're going to talk about a couple more papers, then we're going to pull it all together right quick. So M8 paper, I know we all have it. Most of us stopped using it for years, but M8 paper tells you a lot of information about chemicals. And so I've been trying to make sure people understand that, because I wasn't sure if people really understood. M8 paper, yes, it's designed for chemical warfare agents. Does it work well for that? Not really. However, what it does tell us very well is that if we have an organic chemical, it's going to soak right into the paper. If we have a water-based material, it beads up and rolls off the paper. So I can quickly tell you an organic versus an aqueous solution just by looking at the way it sits on the paper. Okay. Now, when I start looking at the reactions that I see, yes, a G series agent or something like sarin, soman, tabun, they would all give me a gold color of the paper. But we also have all of our alcohols, ethers, nitroalkanes, and some of our things like bleach, ammonia, while not one of those groups, also come in here. Okay, and we start to see those sodium hydroxide. All of these things will give you that yellow color. To get the red color of a blister agent, you're going to see things that are all your hydrocarbons, your organic peroxides, ketones, furans, esters. Do I think you should know what all of those groupings mean? No. But if you have a threat list, you can start pulling it down and then say, what types of esters may I come across in this area? Okay. And then, of course, your amines, your larger amines outside of ammonia, these are the same ones that are going to give you a bit higher of a pH. Also are going to give you a V series, so green type of color on your M8 paper. So when we start looking at that, if my pH was around 10 and it was gold, it may be ammonia, okay? If my pH was around 12 to 13 and it was green, it's likely one of the other amines like ethylamine, methylamine, triethylamine, any of those types of materials. So we're starting to pull those papers together and say, I can quickly start ruling out other things. Same thing here. If I had alcohols, my pH paper is going to be neutral. But isopropanol, methanol, any of these different alcohols are going to actually turn my G series color. And they're also going to start giving me information on my flammability. So different things we can pull together. And then, of course, our KI paper. This is one of those things that you always have on a call. And mainly, one of the biggest uses I use for this is to look at a chemical and say, is it an oxidizer? And when I want to look at a material and see if it's an oxidizer or not, that is actually telling me a lot about whether I'm going to use it in Raman spectroscopy. So when Scott first talked about those detect to identify technologies, so our second stage types of chemicals or materials, I don't want to run something on a Raman spectrometer, which may be putting energy into my sample if I know it's an oxidizer. So I first go through and say, let me just check. And if it's a solid or a solid, I'm going to have to wet the paper to do it. But let me just check and make sure it's not an oxidizer before I start putting a lot of energy in and take a chemical that likes to make things worse and make it really worse. So when I have my KI paper, the color you're looking for is a dark, dark blue. But reality is you'll have some materials that turn it black almost immediately, but then it bleaches white. And that's things like chlorine and bleach that will do that. So chlorinated solvents that are strong oxidizers. When it turns black and generally stays there for a length of time, it may turn white later, but generally our peroxides are doing that. Okay? Oops, sorry. If it turns blue quickly, and we're talking a very different between the black color and the blue color, then it's a standard oxidizer. Still not something we want to mess around with, but not as strong. And if that blue color is really slow, it's a weak oxidizer, something like iodine. So great piece of kit to have, and I use it always before I run a Raman sample. And I've started playing around again with peroxide test strips, and mainly because there's a lot of other information I'm finding, because things that are strong peroxide forming chemicals or some of the other oxidizers and nitrates will actually change these as well. They don't give you the traditional color change you're looking for of the blues and the gray type of black, but they will give you oranges. So when I start looking at things that are turning peroxide test strips orange, then I know I have a nitrate or I have a hypochlorite. I have some other type of oxidizer outside of the peroxide family. So I start looking at that and comparing it back. Now, benzoyl peroxide, if we're dealing with that, is one that I have to add a little ethanol into to get it to change the color, and that's mainly about solubility. But when I start seeing peroxides this blue, and if I'm looking at like a solid or even a liquid that may have some crystals forming around the neck, the materials I start thinking of right away are diethyl ether, isopropyl ether, THF or tetrahydrofuran, or dioxane, because these materials tend to form peroxides at the neck. While they're not peroxides themselves, as they degrade, they form them. And that's where we oftentimes have the issues when we go to open a container and you actually are putting friction because you've created a peroxide at the neck, and now we have to be very careful. So I'm going to walk you through a couple of examples, and I know this is a lot of information, but I want to show you how I take this from the beginning, solid, liquid, gas, and say, let me go through and do my test. So in this case, I've got a liquid. So step one, I'm going to do my rad meter background. I had background only, no threat. My LEL sensor comes up, it's flickering at 1%. So we know right away it's a flammable with a high vapor pressure and a high concentration in air, because that 1% is going to signify hundreds of parts per million up to thousands. Okay, if I have pH that's wet above the liquid, okay, and it's pH 10, but it's at a distance, then I know, again, I have a vapor forming liquid that's basic with a high vapor pressure. Okay, so we know it's a liquid solution that's basic in solution, high vapor pressure. When we have pH wet in the liquid, that's pH 10, just tells us basic solution. We already knew that from the one above. And then if I have pH dry in that liquid and it changes color, then I know that I have a basic water-based solution, remembering that pH change requires water to actually happen. Now, I'm going to do my F paper. Usually I only do my F paper if I have an acidic solution, especially a strongly acidic solution. But for this one, we'll just do it and say, you know what, no response, it stays pink, not HF. Now I'm going to go to my AP4C, and in this case, the nitrogen channel is flashing, and it's flashing in a gas phase sample. Then I know that the vapor above that liquid contains nitrogen. So we now have high vapor pressure, vapor forming liquid that's basic, and it contains nitrogen. We have a PID hitting at 140 parts per million. That tells us it's likely a toxic chemical with an IP or ionization potential less than 10.6 because we saw it on that lamp. The M8 paper turns gold. I'm assuming it's not going to be sarin, but it could be, right? It would give us very different results though. But now if the M8 paper turns gold and we know it's a basic solution, the basic things that turn it gold are ammonia, bleach, and sodium hydroxide. With those, we already know that the vapor contains nitrogen. So we're already pretty well on our road that it's definitely ammonia. If the KI paper didn't change, there's no reaction with starch. Remember, ammonia is an oxidizer. However, it doesn't react with starch in the paper. And then for the electrochemical cells, if we have ammonia over range, that's going to tell us with the cross sensitivities that it's ammonia or it's hydrogen sulfide. So when we take all that together, we know we have a basic liquid with a high vapor pressure that contains nitrogen and its ionization potential is less than 10.6, which puts us to that it has to be ammonia hydroxide, which is off-gassing ammonia at 1,500 parts per million. So to do that, we knew that the 140 parts per million, we used its correction factor, okay? We knew that it was nitrogen container, but the channel was flashing, which meant it was over its maximum. So we knew it was going to be over that, and we used the PID to do the concentration. So quickly figure out it's a basic liquid with a high vapor pressure, contains nitrogen, IP less than 10.6, and now you can figure out everything about it. Now, a little bit more of a challenge. So we now have another liquid, And the rad meter says background only, so no rad threat. You can see I don't like rad, so we're going to skip over rad here. LEL sensor has no response, so we know it's not flammable at the level of concern. The pH is for wet above liquid, no response. Okay, so it's not corrosive. It has a low vapor pressure or both. The pH when it's wet in liquid is around 6. Okay, so slightly acidic. Is it an organophosphate? Is it an aldehyde? Those are things that are generally slightly acidic. Okay, the pH in dry liquid has no response. Okay, not a water-based solution then, because we had a response when it was wet. F paper, still I wouldn't have used my F paper just because I've saved it, but because the pH was not at that 0 to 2, 0 to 3 range. Okay, my AP4C is hitting on the P channel with 1 bar. Okay, 1 bar on my AP4C is going to say very low vapor pressure. If there's phosphorus containing vapor coming off of this liquid, it's at a very low vapor pressure because the P channel is very sensitive. Now, the PID has no response, then I know that my IP is either greater than 10.6 or again, I'm at a very low vapor pressure. My M8 paper turns green, okay? Remember, green is VX, okay? So it's either a V series agent or it's an amine. Remembering that ammonia, while the simplest of amines, doesn't turn green. That's the one that turns gold. So in this case, the KI paper had no change. It stayed white, so no starch reaction. When we start looking at all of these and the E cells, none of my E cells have a response. Okay, so likely very low vapor pressure or no cross sensitivities. So when I look at this one, I have a slightly acidic, non-water-based solution that's not flammable, that is a very low vapor pressure, but contains phosphorus. And when we come back, we're really pushing towards an organophosphate. But do we know which one it is? Okay, so it's slightly acidic, okay, vapor pressure with a V series or an amine. But then when we start looking at it and say that it has phosphorus, not nitrogen, amines are going to have nitrogen. So we now know it's VX, and if it's only 1 bar, it's less than 3.9 parts per billion vapor. So when you start looking at all those things together and start figuring that out, now, does it definitely have to be VX? No, there's probably other organophosphates that may change the V series, turn it green, but VX is going to be our worst case scenario. So that's the one we're going to run with. And now let's go through an example with a gas. Okay, so we're going to come through and say rad meter, background only, no rad threat. Again, Christina hates rad, so we're just skip that. LEL sensor saying it's not flammable, so we're not getting any high levels there. pH, I'm going to do it wet in the gas. No reason to do it dry or anything because there's not enough material there. It's all gas phase. So no response is telling me whatever the gas is, it's not corrosive. Okay, I skip over the others and go to F paper, wetted in air. And again, not HF. My AP4C is giving me 3 channels in the nitrogen channel. Okay, so we know that it's a nitrogen containing high vapor pressure material. The PID has no response, so it's either giving me IP greater than 10.6 or a low vapor pressure. We already know that it has to be a high vapor pressure to be a gas. Okay, the M8 paper has no response, so it's traditionally telling us it's not a chemical warfare agent and not an organic liquid because it's not soaking into it. Okay, KI paper didn't change, no reaction with the starch. And our electrochemical cells for ammonia, hydrogen cyanide, and SO2 were all positive. Okay, from that, looking at the cross sensitivities, it's most likely hydrogen cyanide. Okay, hydrogen cyanide gas could give us all of that. Now, hydrogen cyanide gas is flammable, and this is why I brought this one up, is because if it's only measuring at less than 63 parts per million based upon the AP4C, it's measuring below where it would show up on the LEL sensor at 1%. So that would be around 267 using the correction factors. So hopefully this showed you that just using some of these quick, easy things, reality is I keep charts of what all the different responses could be, and then looking across those and saying, with these things coming in, I use it as a rule out type of approach. So I can quickly rule out flammable gases at higher concentrations. I can quickly rule out corrosive gases at higher concentrations. Okay, and I start looking at all these and I can say, you know what, the material has nitrogen in it. When I look at our general threat list that we have of toxic industrial chemicals of highest interest as a threat to a human, 70% of them have materials I can measure with an AP4C, whether it's in solid, liquid, or gas. A PID can get about 40% of them. It's getting the gases or the vapor-forming liquids, and only those with a 10.6 or less IP. And so they start pulling out all of these things. But this is one of the charts I try to keep up close and personal because I always forget which ones would fall into these groupings. So in this case, remembering it's just a process. So when I look at things that are pH less than 5, they tend not to be flammable. Okay, so I look right away and say, okay, I have something that's not showing up as flammable. It's got a low pH. If I'm below 3, I start thinking my inorganic acids. Below 4, organic acids get added in. In between 4 and 6, I'm usually looking at organophosphates and some of my aldehydes. And then when I get into that range, I can start pulling them apart by using things like M8 paper and say, okay, if I have the organophosphates, are they more towards sarin or are they more towards the VX? Okay, and that's going to start telling us, are they gold or green? And it's going to tell us right away, either way, that it's an organophosphate because the amines, which would also turn it green, are way up here. Okay, so when I start looking at my neutral things, my things that are my ketones, organic solvents, my hydrocarbons, all of those things give me a neutral pH. But most of these things, I can start playing around with Ki paper, M8 paper, the biologicals, I use my protein test kits, and all of those start pulling apart right away when I say pH is neutral. Now, I oftentimes think of anything between 5 and 8 as neutral and start playing around at that point. But once I get above 7, I start thinking about combustible and flammable materials. So I can start coming through and look at things like my alkali hydroxides, my alkali earth hydroxides, all of these different things here, organic peroxides that I may come across, and use my peroxide test strips here. Okay, when I get up higher, I start thinking of ammonia or ammonia hydroxide or cloudy ammonia that we have at home. 10 to 12, again, my organic bases and amines, that should turn my M8 green as well as my pH going 10 to 12. And then as I get to the really high levels, remember my organic bases. And now one thing I do want to remind you, sodium hydroxide and potassium hydroxide at really high concentrations also tend to do that thing where you put dry pH paper in and you see no response. So it kind of like looks oily, it kind of falls right back off of it. And you think, it's an organic. But unless you put the wet pH paper in, you won't see those high concentrations because there's not enough water to work. And each of these things are kind of where I come to my overarching chart of dividing them out into classes and then using my PID and my AP4C to identify exactly which one based upon the readings I'm getting. And your electrochemical cells, obviously. With that, that was kind of what I wanted to talk about today. So, Scott, are there any other things that you want to bring up?
No, I think you did a good job of answering those. Just if people have questions, that would probably be helpful.
Okay, yeah, if there's any questions, I'm going to pull up the questions panel and see if there's any questions. Oh, okay. Looking at, okay, so one of them is, why list pH 8 to 12 for flammables? The most common pH papers will typically show a pH of around 4 to 6 for many organic solvents. Yeah, I usually start anywhere from that normal pH, when I start looking at organics, those are definitely in that flammables category as well. 8 to 12 is where I kind of consider combustible and flammables. But yeah, really, you could actually start looking at some of those. And flammables giving a high of, just have not heard of flammables giving a high pH. Yeah, there's a lot of them that do give a high pH. So can be lots of HF on plumbers' trucks. Ew. Okay, didn't want to think about that, but thanks. And then if HCl is concentrated enough or hot enough, it will turn green with copper filings, just not as quickly as nitric. Is that worth mentioning? Yeah, definitely worth mentioning. It's really going to be at ultra high concentration. So I usually use copper filings for nitric because it is really quick. So, but I keep a little vial of my copper filings, and I buy them off of Amazon. So you can get them pretty close. Is APC utilizing atomic emission bands or any molecular emission bands? What is the wavelength resolution of the spectrometer? Scott, I'll let you go with that one, but it is pretty much atomic emission, I believe.
Yes. And so what we're really doing is we're looking for, we're converting the light energy and then matching it to spectra that we have, for what we, obviously the response that we know that we're seeing with it. Now I have a slide that actually shows the response at different wavelengths. Didn't include it in this presentation, but it's a visible light that we're focused in on because of the sensor. So we're taking the light data, converting that to basically capturing the information and then analyzing that information. So it has to be done in complete darkness in order to analyze that information that's coming off of the flame in order to be able to do that. And then there's obviously a baseline because the flame is automatically normally seen in the response. So we're looking at the flame plus the response. I don't know if that fully answers your question, but hopefully it does.
Okay, I'll wait and see if Noel puts anything up. Have you ever tested the AP4C on the nitrogen channel for isocyanates, such as TDI? And I was trying to see if I could pull up the cross sensitivity, I've got methyl isocyanate right here. So let's go to detectors, and we do have the AP4C calibrated for methyl isocyanate, I can see. So I would have to pull it up, and I can pull it up in a second. Let me go through the other ones right quick and see if one con for peroxide paper does not have a shelf life. KI will last virtually forever. If it does not, it will tell you. Yeah, definitely. Mine started getting spots. Okay. Ben, high pH on flammables was something new for me. Just remember neutral and high. So in ultra high, again, not going to be flammable there. Wet and dry pH on heads-up display on mask. Reality is, in that case, just go with wet, because to get the lower, I know a lot of people do put it on their masks. I generally put it on the arm or something where I can see it better and not lose any of my visibility. The other one, Noel, just curious about wavelength resolution for the AP4C. I know in libs you need a very precise grading to get good data. I don't know.
So that's part of the science. Yeah, that's part of the science on how the system works. Now each channel is independent, and you can have simultaneous present, so you can have more than one channel present simultaneously with the device, but it is primarily on the capture of the full spectrum. Some of that's the proprietary nature of how we do it, so I don't want to go into tons of that. Hopefully you can understand some of that, the nature of it, but yeah, I guess the way to say it is it's a function of the device and the results that you get. So each detector has some variability, so not every detector has the same response. So we have to learn the device in order for it to occur. That's some of the parts of the proprietary nature of kind of how we do it. But it is, I guess the main thing is each response is unique and specific to that element. And so there is not, and we can actually do more than just the elements that we're seeing, which we do for like biological detections, where we add in sodium, potassium, and calcium as additional elements into there. So we can handle multiple elements simultaneously as well. In addition to those, just those are the ones we have chosen because that's what's needed for this type of application.
Okay, and if you can see the screen right now, Noel, this is TDI on the AP4C. So you actually are up towards ideal H when you start seeing it. So let's go to, see if I can move this thing out of here. Okay. It's going to start measuring it around 1.6 parts per million. So when we start going down below that, you're not going to get it at the ultra low levels that you really want, but it will get it below ideal H. Let me see if I can pull up MDI. Okay, and with MDI, you're going to get it, again, it's going to be in the 2-bar range when you get to ideal H, and 1 bar is going to bring you down again to that 1.6 parts per million. Okay, because it's measuring the nitrogen. So yes, we have done both and calibrated it, but you will see some of that. And it's going to be about looking at putting it in as a liquid or solid and measuring it using the crack pipe, really. And I know Scott and I are probably not supposed to call the S4PE a crack pipe. However, that's what it looks like. Okay.
And the funny thing is that's probably one of the things you'll remember about the presentation is the crack pipe. So
yeah, and so no, yeah, definitely you're not going to get PEL, permissible exposure limit measurements for TDI or MDI. You're definitely up more towards ideal H. The least sensitive channel on the AP4C is the nitrogen channel. Otherwise, it'd be measuring so much more. Which don't necessarily want, whereas the phosphorus channel, which we want to be ultra low level, is focused in on those things. But that means its range doesn't go up as high as ideal H. So for some things that are phosphorus containing, it only measures down by permissible exposure limit and not up towards ideal H. So trying to get, and I like to have, when I look at these things, I try to get like a kind of a blend, and I should have put a slide in here, but I usually put in that continuum of interest. So the permissible exposure limit up to the ideal H and even up to the lethal concentration if necessary, and show which detector is hitting in each area. So the AP4C is going to be at that low end usually if it's in phosphorus or sulfur channels. And it's going to be in that mid-range if it's going to be on nitrogen channels. In arsenic, it's just going to depend upon which threat material you have. But when we start looking at electrochemical cells, they can be a little bit lower or on the nitrogens, but will be a lot higher on the phosphorus. When we look at the PID, that's going to cover the broader range, but not as specific for the level. And then the LEL sensor is what we're going to use when we're over 500 parts per million generally before it sees anything. So when you start looking at that, you have different detectors you're going to use to measure for the concentration and change that over into a measurement when you start playing around with that. Yeah, so Noel, in terms of using KI paper, all kinds of false negatives, especially in the laboratory. So we very rarely, activating it with HCl definitely will give you a better result, but it's not operationally always capable in the field. Okay, so some of us do carry, especially those of us that did, I don't know if anybody else is near and dear to my heart, but I'm old. The hazmat kits using the old wet chemistry where we always carried that material and small amounts of hydrochloric in solution that we could use a couple droppers full, wet things up and go with it that way. That was fantastic. A lot of teams just don't do that anymore. What kit do you have, Noel? I didn't know what kit do you do. So let us know on the notes. And then the other one, Kent, sorry, I haven't seen you in days, Kent, but great place to buy paper like pH and K paper. frankly, I buy mine online at Amazon, but I'm usually at the last minute when I'm buying it. Okay, quickchem.com. I'm gonna have to look that up. That's pretty cool. But reality is pH paper, K paper, you can get that from any of the different vendors you use. I know places like Safeware sell it on their, it's kind of the All Cities or US Cities contract. You can buy it there. All kinds of places that you can get that. I end up buying mine last minute. So, but every one of, I think, of the resellers, I think First Line probably sells it, Far West, Safeware, all those different folks.
I think you can get it off a GSA Advantage as well, if you have a GSA contract.
And Noel says he sells them too. So if you, I haven't gone to his website, but it's QUICHEM.com. So QUICHEM, quickchem.com. And then Derek, thanks. So yeah, also look for the 3-packs. Definitely. You would be shocked when I was trying to buy some on Amazon the other day. The 3-packs were cheaper than the individual. Okay, so just remember that. And I always like to get just a little box of watch glasses so that when you want to do any of those different things, you can go ahead and do that in the field. I know we're over time. 12:30 was our cutoff. But if you have any more questions, please throw them on here. And then Scott and I will go back. You can see he's at a meeting in Tampa. And then I am going to hop on a plane to Australia in about a couple hours now. So we will, obviously this is being recorded. We are going to have that up for you. And obviously it won't be in the next few minutes because it takes me a bit to get that all pulled together. And hey, thanks, Derek. I haven't seen you in days either, Showman. So if you, Derek is from Hazmat 101 Consultants out of Orlando, great friend. We work together a lot as well, and Orlando Fire fame. But when you start looking at all of these things, just remember, we're gonna get back to you in a few days this time with more information. That's gonna first have your certificate from Proengin Academy, and then we will also have all of our different information up for you to look at with this video. And then hopefully when I get my act together, I'll get a white paper with the flow charts out for you that I use for identifying unknowns using all these techniques. So with that, thank you guys so much for hanging in with us. As you know, Scott and I love doing this, so watch for our next one. I think we have it scheduled for the end of June. We're looking at one around June 28th, if you're paying attention, at the same time frame. So that's our next goal. Thanks again and stay safe out there, everybody.
Thanks.